Hi, and welcome to the third video of this section. In the previous video, we spoke about k-nearest neighbor classifier. In this video, we're going to take a look at one of the popular classification algorithms, which is support vector machine. First, we will talk about what is special in support vector machine. Then, we're going to talk about the advantages and disadvantages of SVM, followed by knowing more about support vector machine, hyperplanes, and support vectors. Then we will discuss the optimal hyperplane. Let's begin this video with an overview of SVM. Support vector machine is famous for classification problems, but we can use it for regression analysis problems too. This is one of the main advantages of learning support vector machine. SVM was originally invented by Vladimir N. Vapnik and Alexei Chervonenkis in the year 1963. Coming to its advantages and disadvantages, SVM works well for high-dimensional spaces and is more effective when the number of dimensions is greater than the number of samples. We also have some disadvantages in applying support vector machine to data mining problems. As for example, SVM does not directly provide probability estimates like many other classification algorithms. The performance is not good when the number of features is much greater than the number of samples. The key concept of SVM lies in the understanding of hyperplanes, as SVM is formally defined as classifier for separating hyperplanes. Let's talk about hyperplanes and support vectors, as these are the key things in understanding the SVM algorithm. Hyperplane is in a high or infinite dimensional space, which could be used for classification, regression, or other tasks. Intuitively, a good separation is achieved by the hyperplane that has the largest distance from the nearest training data point of any class. Let's consider a 2D plot for a better understanding of SVM. Suppose we have 2D points that belong to two different classes. As we have seen the same kind of plot in the previous video, one class is circles and the other is square boxes. Now, our aim is to find lines to separate these two classes. Let's call them hyperplanes. We could separate these two classes with two hyperplanes, H1 and H2. We can add some more hyperplanes which successfully separate the two classes. Here we have H1, H2, H3, and H4, which are basically the hyperplanes that are separating the two classes. Here on the screen, we can see that one circle is touching one of the hyperplanes, and we can observe that the two square boxes are near another hyperplane. These are called support vectors. Now, the main question to consider is, out of so many hyperplanes, how to select the best hyperplane, which is also known as the optimal hyperplane. Before discussing more about optimal hyperplane, we need to know about another keyword in SVM, which is margin. The final optimal hyperplane will have hyperplanes on both sides. You can observe this on screen. Now the margin is nothing but the distance between the optimal hyperplane and those hyperplanes. The hyperplanes, which are on either side of the optimal hyperplane, should be as close as possible to the support vectors. To get the optimal hyperplane, we have to consider the hyperplane, which has the maximum margin value out of many other hyperplanes. Now, let's talk about mathematical stuff in calculating the optimal hyperplane. As a reminder, the hyperplane or line equation is f of x equals alpha plus beta x, where alpha is the bias value and beta is a vector containing weights such as w1, w2, and so on. If you remember from our previous slides, we've seen many hyperplanes used to separate two target classes. So we know that we'll have a hyperplane equation for each hyperplane. Out of all the hyperplanes, we have to choose the hyperplane which satisfies equation 2, which is generally the magnitude of the line equation. It should be 1. Now, from geometry, the distance between the line and the point is equation 3, where norm of beta is the square root of the square sum of vector point in beta. For equation 2, we know that the numerator is 1, as we have two margins on either side of optimal hyperplane. We will have two distances, so the sum of two margin distances will be equation 4. Now the problem is to maximize the m. This is to find corresponding weights that are having maximum values. Once we have the proper weights that maximize the m values, we can use those weights to find the optimal hyperplane. This is how Support Vector Machine works. SVM works just as well in higher dimensions with hyperplanes. Time to summarize what we've learned in this video. First, we spoke about the Support Vector Machine and its inventors. Then, we discussed hyperplanes and support vectors with a 2D plot graph example. Then, we spoke about finding the optimal hyperplane. We also discussed the advantages and disadvantages in the usage of SVM. That's all for this video. In the next video, we're going to implement the logistic regression model to solve one interesting problem. See you soon then!